All right, let's jump right into this explainer on high-voltage battery management systems. Today, we're zeroing in on a genuinely terrifying scenario, the catastrophic failure of cell voltage acquisition. If you've ever wondered exactly how modern electric vehicles prevent battery fires when their internal sensors suddenly just stop working, well, you are in the right place. We are going to unpack the incredibly robust, multi-layered defenses that engineers rely on to combat the P0A04 and P0B3D diagnostic trouble codes. So, what are the stakes here? Well, that quote really hits the nail on the head. Cell voltage is literally your last safety barrier. If the battery management system, the BMS, loses its voltage sensors, the whole system goes completely blind. Think of it like driving down a highway at night with no headlights. Without accurate cell voltage readings, the system completely loses its ability to stop overcharging or over-discharging. And in a high-voltage lithium-ion battery pack, going blind like that opens the door directly to thermal runaway and a potential fire. Here is our roadmap for the breakdown today. We'll start with root cause analysis, move right into hardware and software defenses, and then cover DFMEA, design prevention, PFMEA, process control, and finally, DVP&R, mass production validation. Okay, let's get into Section 1, root cause analysis, the enemies of the battery. To build a solid defense, we first need to know exactly what we're up against, right? We're looking at 4 distinct dimensions of failure: chemical, physical, electrical, and crosstalk. Now, on the chemical front, there's this wild phenomenon called the hose effect. Imagine a tiny, almost invisible leak of acidic electrolyte from a battery cell. Through capillary action, this highly corrosive acid literally climbs right up the microscopic pores of the wire casing. It travels all the way up to the main board, eating away at the delicate chips and copper traces, creating physical breaks or even localized short circuits. It's basically a slow-moving poison. But it's not just chemistry. We also face the slow, grinding mechanical fatigue of physical threats. Think about the constant, high-frequency vibrations from the road causing microscopic cracks in the solder joints, or the slow backing out of connection pins, which is known as terminal pushout. Then we've got electrical threats, like a sudden high-voltage surge during maintenance that can instantly fry the multiplexer chips. And finally, crosstalk. When a wire breaks, the disconnected channel might drift to 0 volts, or totally max out to a fake 5 volts, which completely throws off the readings of the perfectly healthy adjacent cells. Moving on to Section 2, hardware and software defenses, the system architecture shields. So how do we fight back? Well, the battery's analog front-end chips use a brilliant feature called open wire detection. The hardware actively searches for trouble, almost like a submarine using a sonar ping. In the background, it injects tiny pulses of microcurrent into the channels. If the wire is perfectly fine, the battery's massive capacitance easily absorbs this tiny current without so much as a blip. But if that wire is broken, that microcurrent has absolutely nowhere to go. The impedance spikes instantly, and the hardware flags a sudden drop to 0 volts or a max saturation, instantly catching the broken connection. And then we have our software stepping in as the second line of defense. It constantly analyzes the dynamic voltage rate of change, or dV/dt. Normally, a battery drains or charges in a super smooth, incredibly slow, flat curve. But a broken wire? That produces a violent, sudden cliff drop or a massive spike. By continuously monitoring this rate of change, the software can instantly filter out random noise and accurately declare a true physical break. Now, what if a failure actually happens while you are cruising down the highway? This fail-safe sequence takes over immediately. The moment the system confirms that fault code, it enters a strict voltage fail-safe mode and heavily derates the power output to protect the battery. It instantly kills pure EV mode, forcing the vehicle into a hybrid engine-driven limp-home state so the driver can safely pull over. It's a highly calculated, strictly controlled shutdown. Which brings us to Section 3, DFMEA, design prevention, engineering the blueprints. Look, because a blind battery carries a massive severity score of 8 or even 9 out of 10 if there's a fire risk, engineers literally have to design physical workarounds for these threats right into the blueprints. To fight vibration fatigue, they don't just use standard straight traces. They use curved teardrop shapes on solder pads and S-type geometric bends to absorb mechanical stress. To fight electrical surges, they add TVS transient suppressors that act like electrical airbags. And to fight wire breakage, they use dual wire bonding. If one microscopic aluminum wire snaps from fatigue, a redundant second wire is right there to carry the signal and save the entire system. Let's shift gears to Section 4, PFMEA, process control manufacturing controls. To actually block that nasty corrosive acid hose effect we talked about earlier, factories mandate 100% automated vacuum conformal coating over the circuitry, creating a physical barrier that acid simply cannot penetrate. And this is backed up by incredibly intense scrutiny on the assembly line, 3D automated optical inspections, solder paste inspections, and 3D X-rays hunting for any hidden microscopic voids. Every single weld uses closed-loop statistical process control, and everything gets subjected to inline pull tests to guarantee a perfect physical bond before it ever leaves the factory floor. Finally, we hit Section 5, DVP&R Mass Production Validation, the ultimate trial. Consider this exact number, 500 milliseconds. That is the absolutely critical debounce delay window. If the hardware thinks it detects an open wire, the software waits exactly 500 milliseconds before doing anything. Why? To ensure the system just ignores a random split-second jolt from hitting a pothole and confirms it's actually dealing with a true, permanent, single-channel open wire. But what if multiple channels fail all at once? That points to a massive, catastrophic physical shear. In that case, the system absolutely does not wait around. It gets a mere 100 milliseconds. That is the strict fault-tolerant time interval limit to execute a hard shutdown, instantly triggering the relays to physically isolate the high voltage before disaster strikes. And you have to think about the brutal endurance timeline this hardware goes through. We're not talking about a quick stress test here. We're talking 300 straight hours of 3D random vibration, paired with wild thermal shocks from -40 to +85 degrees Celsius, just trying to snap those S-type stress flex cables. And that is immediately followed up by 500 hours of localized acid drips in an extreme 95% humidity environment, specifically trying to eat right through that conformal coating. The passing metrics for all this? Totally unforgiving. I mean, after all that torture, microscopic cracks at the weld joints must stay under 10 micrometers. Contact resistance can barely shift at all. And the leakage current from the acid trip test rigidly held under 1 milliamp with absolutely zero chemical crystallization allowed. This is exactly how engineers prove that the protective coatings and stress reliefs are genuinely battle-ready. All right, let's wrap up this explainer with one big question. Considering everything we've just uncovered, from the microscopic threat of capillary acid leaks to those split-second hardware reflexes and the brutal 500-hour torture tests, when your battery goes blind, is your system truly ready to fail safe? Because in high-voltage engineering, just assuming you're safe is never enough. You literally have to engineer the proof. Thanks for diving deep into the anatomy of battery defenses with me. Keep exploring, and I'll catch you on the next explainer.